The word stoichiometry comes from the Greek words stichion, which means element, and metron, which means measure. So it literally means the measure of elements. In practice, it is the relationship between the numbers of moles of reactants and products in a balanced chemical reaction. The law of conservation of mass requires that the mass of the products of any reaction be the same as the mass of the reactants. Therefore, the number of moles of each type of atom must be the same on both sides of the equation. You can see that this reaction is not balanced because the reactants side has 2 hydrogen atoms and 2 oxygen atoms, but the product side has 2 hydrogen atoms and only 1 oxygen atom. We can change the number of product O atoms to 2 by increasing the stoichiometric coefficient of water, but this unbalances the number of hydrogen atoms. But if we now increase the coefficient of hydrogen to 2, we can finally balance the reaction with 4 H atoms and 2 O atoms on each side of the arrow. Balancing the reaction for combustion of propane is a little bit more challenging. We start by comparing the number of carbon atoms on each side. To achieve balance, we need to multiply the product CO2 by 3 to match the 3 carbon atoms in the reactant, propane. Now the carbon balance is okay, but the hydrogen and oxygen are still unbalanced. Looking at hydrogen now, we can balance it by changing the stoichiometric coefficient of water to 3. Now there are 6 hydrogen atoms on each side, but the oxygen is still unbalanced. We left the oxygen for last because the reactant is elemental oxygen, and its coefficient can be changed to achieve oxygen balance without disrupting the balance of any other element. On the product side, we have 9 oxygen atoms, so we need to change the coefficient of O2 to 4.5 to achieve the oxygen balance. Technically, this reaction is now properly balanced, but it is conventional to adjust the coefficients so that they are all integers, and we can do this easily by multiplying all of the coefficients through by a factor of 2. So here is our completely balanced chemical equation with 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms on each side of the arrow separating the reactants from the products. Sometimes chemical equations are decorated with symbols to indicate whether the compound is a solid, liquid, gas, or perhaps dissolved in water or aqueous solution, as indicated here by the symbol AQ. When we dissolve sodium chloride in water, it separates into dissolved sodium ions and chloride ions, because all sodium salts are soluble in water. Similarly, lead nitrate dissolves as lead ions and nitrate ions because all nitrate salts are soluble in water. But when lead ions and chloride ions encounter each other in solution, they precipitate as a white solid, lead chloride, which appears at the bottom of the container, as shown here. Notice that 2 chloride ions are required for each lead ion in order to balance the mass and the overall charge on both sides of the equation. We have written the equation for the precipitation reaction as a net ionic equation in order to focus attention on the chemical bonds that are formed between lead and chloride. The total ionic equation shows the sodium ions and nitrate ions on both the reactants side and the products side unchanged. So we call these spectator ions in the reaction because they are not involved in the making or breaking of any chemical bonds. Another type of solution phase reaction is between acids like phosphoric acid and bases like potassium hydroxide. Both compounds dissolve in water, but the hydrogen ions from the acid combine with the hydroxide ions from the base to form liquid water. This is the only bond formation process, so only these species are included in the net ionic equation. The thermite reaction between iron oxide and aluminum is a spectacular demonstration of heat release. The liquid ion produced is so hot it reaches its boiling point. This reaction is used to weld iron train track rails together to eliminate the gaps between the rails for a smoother ride. The stoichiometric coefficients in the balanced reaction are useful for determining the mass of each reactant required for efficient production of the molten iron. For example, if we need to produce 1 kilogram of iron for welding 2 rails together, we start the calculation by converting the product to moles. This is done by dividing 1,000 grams by the molar mass of iron to get 17.9 moles. Next, we use the stoichiometric coefficient from the balanced reaction to determine that we need 17.9 moles of aluminum, because the coefficients of iron and aluminum are the same, but we need only half as many moles of iron oxide, because its coefficient is 1 instead of 2. Finally, we convert the moles of each reactant to mass by multiplying by their respective molar masses to get the mass of each reactant that must be weighed out and mixed for the reaction. Another colorful demonstration is the chemical volcano produced by mixing potassium permanganate with glycerol. Suppose we simply mixed 100 grams of KMnO4 with 50 grams of glycerol. Which reactant would be used up first, and how much of the other would be left over unreacted? To determine this, we first need to convert to moles by dividing each mass by the appropriate molar mass. We can see that there is a somewhat larger number of moles of potassium permanganate than glycerol. But looking at the stoichiometric coefficients, we see that for every 4 moles of glycerol, we need 14 moles of KMnO4 for the reaction. We don't have the required 1.9 moles of KMnO4, so the permanganate is the limiting reactant. If all the KMnO4 reacts, it requires only 0.18 moles of glycerol, leaving 0.36 moles or 33 grams of unreacted glycerol. When chemists synthesize molecules in a laboratory or in a chemical production plant, the efficiency of the process is rarely 100%. Let's take the synthesis of trinitrotoluene, or TNT, for example. If we start with 100 grams of toluene, we might recover only 218 grams of TNT as product. What is the percent yield of this reaction? We can calculate the theoretical maximum mass of the product by converting to moles, making any adjustment for stoichiometric coefficients, and then back to mass by multiplying by the molar mass of TNT. Thus, if the reaction were perfectly efficient, we expect to get 246.5 grams of product. But we only got 218 grams of product, so we calculate the percent yield by dividing the actual mass by the theoretical maximum mass and multiplying by 100%. In this case, the percent yield is 88.4%. We have seen that the molar masses of compounds are useful for converting mass to moles and back again. But the stoichiometric coefficients of the balanced reactions are also important for determining the mole ratios of reactants and products. Remember that balancing reactions is a requirement imposed by the law of conservation of mass. So be sure that every reaction has the same number of atoms on each side and the same overall charge of ions on each side. Only the bonds between the atoms and ions are rearranged in a chemical reaction. Changing the atoms themselves is the domain of nuclear physics.